will try to explain this idea of rocket engineering of quantum materials. And in this lecture, I'll try to cover what we have written in this review article, which was published in Annual Review of Condensed Matter Physics in 2019. So, before going to the main part, let me give you a short advertisement for our opening position in our group. Actually, this is a relatively good postdoc position opening, which is like a 4-year postdoc starting 2024, so next April. And this is a project-oriented position, and the project is related to electrons in strong magnetic fields. Okay, so actually, in our institute, so this is a picture photo of ISSP, and behind this institute, there's a big magnetic facility, and they can produce up to 1,200 tesla, which is the strongest in the world. And using this instrument, we're trying to study many new aspects of electrons in magnetic fields. So people who have maybe background with quantum or strongly correlated electrons, or maybe proposed or modules, you are strongly welcome. Thank you very much. So then, let's go to the main part. So, in today's talk or lecture, let me set the goals. Now, we have many new quantum devices that are driven by external laser fields. And we'll pass here. So, as for new devices, okay, let's think about the future of electronics. So, you know that the electronics right now are mostly working in the gigahertz region, which is actually coming very, very slow. Instead, if we use strong laser pulses, the electronics can become as fast as picosecond. So that's like 10 to the 6 times faster than the current electronics. And using the idea of showcase theory, we can invent and design new devices which will operate and use some current generation and so on in the picosecond time domain. Also, just last year, there was a very interesting experimental paper from the group in Korea, where they realized a flow state in a superconducting system. So this is a group of employees, and they found that they can introduce super flow Android bounce in a very interesting thing about this experiment is that it is a continuously driven system. On the left side, this experiment Hamburg Max Planck already group in Hamburg, it was a pulse field. So this effect of the laser-induced state only lasts for 2 picoseconds. But in the experiment in this Korean group, this is a continuous steady state. So we can realize a very low temperature flow state, which is a very interesting, I think this is a milestone experiment in the field of flow electronics. Okay. So with this introduction, then we start to move to the theoretical part. Okay. So I have many reviews down here, and so I learned that I'm going to share this slide with you. So I put all these reviews here so that you can download them later when if you're interested and want to read these reviews. As for for this upper part, so yeah, here I try to illustrate when we would expect to see appropriate physics. So you see this red line, straight line. This is so this red straight line. This is the laser pulse applied to the material, and this blue line is some schematic view of the state of the system. And you can see that initially you're in the ground state, but the laser will excite your system, and eventually your system will be in something known as a appropriate steady state or pre-thermalized state, and this will last for a very short time. And after the laser pulse is gone, the system will relax. This relaxing process is also very important. But in today's talk, I will basically focus on this laser-driven part. Then, this is still part of the introduction. I want to start my talk with a very simple example. Actually, this is the simplest example. Thinking about the electron escaping from the atom. Let's imagine that I have a hydrogen atom, so one electron orbiting around the nucleus. And then you can apply an electric field. So this problem has been studied by many researchers in the old days. One famous researcher was Herrlich, who studied this problem in 1965. And the setup that we use is very simple. We have a traffic confining potential, Louis, and just study a Schrödinger equation, some one particle problem with this electric field. This electric field is oscillating, so it's an ACP. So in this problem, I want to illustrate which regime the appropriate physics will take place and in what regime other effects will kick in. Okay, so importantly, we know that if we have a confining potential, then this blue wave function, so this blue wave function, the green wave function. So let's imagine this is the lowest state, and we're interested in how we can excite these electrons from here to outside of this confining potential. Okay, so one important parameter is the so-called penetration depth, or the overall radius we have here. It's typically the size of our wave packet. We can also think that this is how long my wave particle can travel inside a potential. Also, we have this gap delta, and then let's imagine that our photon frequency omega is smaller than this delta. Omega is smaller than delta, and let's imagine that our electric field E is strong enough. So this is the setup. Then, for Herrlich, so he studied this problem. Actually, he found an analytical solution to this problem and found out that you have two limiting situations. The first situation is where the frequency omega is very, very low. So my electric field, so my potential is oscillating, but it's very slow. So at one snapshot, so at some time, my potential will look something like this, the left picture, and I can tunnel through this barrier, through this potential. Tunnel through this potential and go to the other side. And the other limit is where my delta is relatively large. My omega is relatively large. After absorbing several photons, I can escape to this plane wave state. Okay. So this is the two limiting situations, and the left situation is called the tunneling regime. The right one is called multi-photon regime, or multi-photon excitation, which has really resemblance to appropriate physics. also, so if you're interested in this problem, you might know this famous parameter called Kelvish parameter. This is often called given by gamma. It's the ratio between omega divided omega and z times e, where z was this Compton wavelength, the size of this wavelength length. Okay, so what's the physical meaning of this Kelvish parameter? It's actually just counting the ratio of the two arrows, green and black arrow. What's this green arrow? This green arrow, you can see on this left side, I have three green arrows on this side. This arrow, the length of the arrow is given by the penetration depth z. And so it's how long my quantum particle can tunnel through this potential. So I can tunnel 3 times penetration depth. So my tunneling probability will be given by how many arrows I need to go through. So that's an exponential decay. On the other limit is a situation where I have this black arrows going upward. So I have 1, 2, 3, 4 arrows going up. In this situation, I absorb 4 photons to be escaped. This situation, my tunneling, the probability of escape is given perturbatively, where I have this E, and the power would be the number of photons I will absorb. So that will be delta divided by omega times 2 plus its probability.
I'm sorry. The C will also depend on the strength of electric field, right?
Z. Okay, so here the assumption is that this Z is basically the same as the one in the original situation. So I already have my penetration in the state without the field. So I define my Z here. And it's like the size of my wavelet. Of course, to be more accurate, as you say, since my potential shape has changed, my penetration depth should be modified. But that's a higher order effect. It does exist, but here in this very crude approximation, we don't see that effect. Okay. So after this consideration, so this is like something like a phase diagram of this escape problem. So in this horizontal direction, I have omega. So with larger omega, my photon energy is higher. It's easier to have this multi-photon escape. Of course, if omega is larger than the gap, we can have a one photon excitation. That's the easiest way to escape. On the other side, we have small omega but large E. This is a tunneling regime where I have a tunneling like this. Okay. So this is the situation where I have this one electron core. Now, in quantum materials, we would be interested in extending this idea to crystals. So what do I mean by crystals? So we know a lot about crystals. This slide is to remind us about the crystals. So basically what we have is a theoretical potential. So and many atoms are there, and let's focus on the band. So we have many atoms and our electrons will start from a band. So for example, if I have a honeycomb lattice, as in graphene, I would have this kind of band structure, and we can find two-dimensional Dirac cone near the K and K prime points. And the effective low energy model there would be the two-dimensional Dirac Hamiltonian, which I write here explicitly using Pauli matrix, sigma x, sigma y. And then I also added this sigma c term, which is the gap term. In the original graphene, this gap term is 0, but I just put it because this gap term becomes very important in the talk. I also have this sign theta, which is the hierarchy of the two-dimensional graph system. It's either plus or minus, and in form of this sigma x term. And in graphene, you have two Dirac points with opposite hierarchies. Okay, so then, so this is also like just to remind us about the rock wave function. Okay, so what we know is that the wave functions inside this periodic systems are described by rock wave functions. So if I write my wave function like this with a crystal momentum k and the position x, actually it's basically a plane wave solution. So I have this exponential I kx and this two-component vector. I'm just focusing on two bands, and this wave function is extended in our crystal. The Schrödinger equation that describes this system is given by something like this, which is written in the momentum space. Okay. Then, now still continuing this introduction. So now, again, I want to go back to this atomic physics and think about applying this electric field. So I already discussed this in the first part, in the this example. But let's think about bands. So if I have this confining potential, I can have the lowest state and the second lowest state. It's like a S or P or D orbitals in an atom. And applying this electric field, you can have a transition. So excitation from one state to another. So this transition is described by a transition probability in this formula, which you would sandwich the operator x. Okay, I have this operator x because it was in this
question.
Yes.
So in principle, like when we consider something with a band, shouldn't the energy gap shrink to like it will like change as the system size change, right? If it is like literally like graphene, this will be gapless. So you are focusing on insulator at this moment, not really graphene.
No, it can be just focusing on like here in graphene you can have a point which is resonant, but yeah, here it's more general. It's it can be a metal or an insulator, and depending on your frequency omega, you have a resonant excitation between the occupied band and the unoccupied band.
I see.
It happens in a metal or an insulator.
Let me just ask my. I just want to make sure, like, what are the states that you are considering? Is it like deep in the atomic limit, or it is like that nearby the valence band? Because if it is nearby the valence band for graphene, it will be like a gapless excitation, right? But if it is, like a S electrons for graphene, then it will be gap. So which situation is your right now?
Yeah, currently I'm not going to that detail. I'm just trying to explain what kind of coupling we have to think, and from more general, broad, like a simple example.
I see. So in general, EN and EN could have some dependence on size.
Yeah.
Okay.
That's true. Okay, thank you very much. I have my small pointer. Okay, good. So one more thing we notice is this. Okay, so now I'm sandwiching my operator x with two different states m and n. This is used as a transition dipole. It gives the how strong I can excite from this state n to the excited state m. You also notice if I sandwich the same operator x with the same state, n and n, it gives the central position of this wave packet. Like the central position of this green wave packet is given by the sandwich of x. Okay, so this kind of hints signals something interesting, which in the next slide. Okay, so we think about the same situation, but now in a crystal. So let's imagine that this is a two bands in a graphene or Dirac system, and I'm thinking about the excitation from here to there. Again, okay, so I want to calculate this quantity, x, sandwiched by m and n. But then there's a big problem. So the big problem is that this operator x is not well defined in an infinite size periodic system. You know, x will be like positive infinite and negative infinite if I have a very big system. Instead of applying x, what we use is this derivative of momentum k, I del k. So this replaces the transition dipole originally in an atomic system to the so-called Berry connection in crystal systems or periodic systems. And this wave function is our Bloch state. So in this slide, I just wanted to highlight that in the physics of laser-driven quantum material, this Berry connection. Okay, so I'm kind of assuming that you have some knowledge about the Berry phase and Berry connection. It's the same quantity. It's a derivative of momentum sandwiched by the states. But then one difference is that my state here is n and m. So it's an off-diagonal Berry connection that becomes very important in this laser-induced phenomena. Okay. So also, so now I will explain these two very important gauges in the physics of electric fields. So up to this point, I have been talking of using this dipole gauge, where I have this original Hamiltonian T square plus potential plus E dot x. Yeah, this is called dipole gauge. Okay, so if we move to a periodic system, so lattice system, we can use a similar expression, but using the language of Bloch states. The Schrödinger equation looks like this, where this H is the Bloch, the Hamiltonian for the Bloch state. But then I have this coupling to the electric field as a E. So this is the electric field, and A. A is the off-diagonal Berry connection, which is represented as a matrix like this. So this is the basic starting point when we study laser-induced phenomena. But then there is another gauge. So starting from this dipole gauge, which have E dot x, I can move to this so-called time-dependent gauge using a gauge transformation. So instead of this potential, which is position dependent, I can move that to this gauge potential. So from the scalar potential, I can move the effect of the electric field to the gauge potential A of t. Now this A of t becomes time dependent. So a time dependent gauge field. So it looks, okay, the transformation is given by this. So you just time integrate your electric field and obtain your gauge field. And then if you go to the Bloch states, so periodic crystal, now the Schrödinger equation becomes very simple. I have a Hamiltonian, but then my momentum is going to be shifted by A. This is really just changing this P plus A to K plus A, where K is the crystal momentum. And then in my talk, I will mainly use this time-dependent gauge because it's easier. I also note that the two different gauges, you can do some calculations, but if you do some approximations, like a truncation, the result can be very, very different. In many situations, the dipole gauge is good for doing perturbation theory in E. On the other hand, if we want to do like a Fourier physics or tunneling, I think this time-dependent gauge is more useful. Okay, then this is the last slide of my introduction part. So this, okay, to set our stage. So in my talk, basically I use, sorry, it moves a lot. Okay, so I use this tight binding model. So the tight binding model, I have a lattice and a fermion operators on each side and a hopping parameter. It's called J, but the time-dependent gauge, I have this Pierce phase A dot B. So basically, this is the gauge field. The difference. Okay, so the product of the gauge field and this lattice displacement. I put that phase on top of this exponential. Okay, so and most of my talk, or like 90%, it's non-interacting. But when I have interaction, you can have like a Hubbard type local interaction. Okay, so that was the first part, and now I will slowly move to the main part of this lecture. Okay.
So when you consider this formally, does that mean that the system that triggered is not going to affect the gauge field that you consider?
Yes. Okay. So there was a question. So about the back reaction effect. So when there's a excitation by the electric field in the system, there will be a current generated by that electric field, and the current will generate an radiation. So your current can emit electric field, and that electric field will generate the next current and so on. In my talk, just for simplicity, I will neglect all those effects and just treat this gauge field as an external parameter or something that is fixed by our hand. This is a good situation when we have a very strong laser field. The field generated by the material is usually much weaker compared to the external laser fields. On the other hand, if we want to study like a more weak field or materials inside a cavity where those current or field generated inside the material becomes important, then this would be a bad approximation, and a different approach should be taken. Okay, thank you. Okay, good. Now, okay, so yeah, I have, okay, so very similar to this phase diagram that I showed you for the atom system. So I have a phase diagram for quantum materials where I have a frequency here and an electric field here. And here, okay, so I have many words. I think the people in the back may not be able to see it, but the most phenomena I'm going to explain it during my talk. But this, okay, as for the color, so this side, the right lower side, this part, it's mainly, you can think it as a multi-photon Fourier process. And then on this blue side, people start to see tunneling effect. This is where the Fourier picture breaks down, and we have to develop new ideas. Okay. I also mentioned one experiment trying to observe this crossover between this multi-photon to tunneling regime, which was done recently in David Xie's group in Caltech. Okay, so I cannot go into detail, but they just saw some, okay, so this is E, electric field, and what's plotted against it is the carrier excitation. Okay, so if I go back, sorry, once, right? So increasing the strength of E, like going from here to there, the multi-photon property and the tunneling property will cross over. And usually this can be seen as a very mild crossover. So the low field is like multi-photon, where the excitation is given by a power law behavior. So in the beginning, I mentioned about Caradish's work, where he showed that multi-photon process excitation is power law in E. And in the tunneling regime, it's an exponentially suppressed phenomena. So you would have a tunneling from the lower band to the upper band. Okay. Actually, this experiment was done for a multi-insulator, and it's not like a band, just a band insulator. It's a multi-insulator, but the basic physics would be very similar. Okay. Then I'll move to this Fourier physics. Okay, so now, so this was the goal of today's lecture. I'm already done with the zeros part, and I'm moving to 1, 2, 3. So remember, we're now trying to understand the Fourier physics. Should I continue? It's okay. It's okay. Okay, so, sorry, no coffee break. Okay, so I hope this works. Yeah, good. Okay, so yeah, this is like a very famous example in the Fourier community. Everyone who learns Fourier physics should understand this Kapitsa pendulum first. So you know that a pendulum, usually the stability point is down there, but when you oscillate it, you have an additional like a quasi-stable point up here, as you can see in this YouTube video. Yeah. So in today's talk, I will explain how to understand this phenomena by very simple calculation. Okay, oh, sorry. Next, then that was the classical example. Okay, so the idea of Fourier physics, you can apply it not to, okay, so even to classical systems or quantum systems. So here, this is an example of a quantum state. I hope you can see this Hamiltonian. So this is a one-dimensional lattice system, and I have a hopping, and then I have this Peier's space. The situation is that I'm having a AC electric field along the direction of the chain. So this is the chain, 1 to 50 sites, and I'm putting one electron in the middle. And this is the phase, but I'm turning on my field at time 0. So initially, I don't have the AC field, but after time 0, I turn on my electric field. And yeah, you can see that the motion have stopped. This is a phenomena which I will explain later. This first discussed by Dunlap and Kenkret in the 1980s. So this is another example of a lattice quantum Fourier state. It's about a Fourier topological insulator. So if I have a graphene and apply a circularly polarized light, so this is another video. So I'm putting one electron at the edge of a two-dimensional honeycomb lattice, and my honeycomb lattice is a circularly derived. I have a circularly polarized laser field on this lattice. You can see that there's a chiral edge state. So my wave packet is moving around the edge like this. This is very similar to the chiral edge state that you have in a quantum core state, just like this green arrows around here in this illustrative picture. Okay. Yeah, again, in this talk, I'll try to.
This is a two-dimensional lattice.
Yes, this is a two-dimensional honeycomb lattice, and I put one electron. So very similar to this. I just put one wave packet here and release it. I have a circular polarized laser field introduced as a higher space. And you can see that there's a wave packet going around. There are some wave functions that go inside the bulk as well, because this is not, it's not a flat band system, but it's has some dispersions. Okay. Then this is an experiment which was done in MIT in 2013. So this is a time-resolved RPS experiment done in Newgetics group. I got this movie from them. So so you can see. Okay, so what they can do is to show a movie. As you can see, this movie is about electron. So this wine glass is the two-dimensional Dirac cone. The electrons in a two-dimensional Dirac cone at the surface of a three-dimensional topological insulator. Then, so initially, I have a Fermi surface here. And then applying the laser, you see some excitation. So something blowing up around here. This part, the right-hand side is like a slice. And you can see these, in the slice, you can see these replica bands, these V-shaped replica bands going up. Actually, the distance, energy distance between one replica to another is given by the photon energy, omega. So it's like the situation that the states go up, up, up by omega. Yeah. So the question is, why can't we see so clearly down here? I think it's a contrast problem. So in a very similar way, there should be a hole-like band down here. But I think it's buried inside this electrons, and it's really like a contrast. They don't have the good contrast. So first of all, you can see that near the Fermi energy, these bands look very clear. The Fermi energy is up here. And if you go away from the Fermi energy, it becomes blurred more and more. So I think that's one reason. Okay, then some recent devices. Actually, I already showed you in the previous lecture, like introduction part. So people can apply laser to graphene and turn it into a quantum Hall state. And since in this device, they have a voltage drop, so a static voltage in this direction, when they apply this pulse laser, there will be a current perpendicular to the static voltage. And that current is plotted like here. And you can see that this current changes, and its width is within few picoseconds. So basically, this is the time scale of the pulse of the laser field that they apply. And this also I mentioned this experiment, a Fock-Andreev bound state, where they can see. Okay, so the great thing about this is that they see side bands. Side bands moving up here, and the energy difference is a few milli electron volt, which is very small. And as I said, this is a continuous Fock state. Okay, now I want to move the theory part. So, but then I try to be very paleological. So if you have any questions, please ask me a question. I'll try to make it very clear.
Quick question about the previous introduction. So when we drive a system, if it is not really in the localized space, in principle, you will have some heating effect, right? So especially if it is triggered by very strong field. So in those experiments, are these complications important, or maybe it is not really important?
Heating is extremely important when the field is very strong. And that's one reason that in this ultra-fast experiment, they use a very short pulse. So they apply this short pulse once in like millisecond, like a long time. One pulse comes, and then before the next pulse, the system can cool down. If you have so many pulses or a continuous laser, typically this graphene sheet will burn up. That was the consensus. So everyone thought that Fourier physics cannot be used in a continuous way. But then this experiment was done, which surprised all the community. I think this is still very controversial, in my opinion. But it seems that they see a Fourier state in a continuous situation. So they don't use laser. Instead of a laser, so you can see this device here. So yeah, I learned from them that they have some antenna up here. It's not shown in the picture, but they would put some antenna up there, which will emit microwave to this device. And it's exciting the system all the time. But then this is an open system. So the heat and the energy injected into this device can be absorbed to the device quick enough that you can have a steady state. And of course, steady state is important to have so this is a superconducting state. The transition temperature is like 10 Kelvin, so, and the temperature will not go beyond that temperature. Actually, you can see the reason that they turn off. So this is the strength of the field, and they quit the experiment around here. If they go further, the superconductivity is destroyed because of heating. But before that, they can see this sideband formation. And they're very deeply in the non-perturbative Fourier regime. Yeah, this is a very surprising experiment. Yeah.
Could you briefly explain what's the Andreev?
Yeah, Andreev bound state. Okay, so the situation is I have a superconductor, so graphene and a superconductor. So two superconductor outside and graphene in the middle. And Andreev bound state is a state where my electrons inside this normal part, they have a deflection between this normal and superconducting regime, which is an Andreev reflection. And you do this many times, and inside the normal state, you get this like a bound state. And the important point about this bound state is that it has a very sharp peak. This is a very sharp peak, and you can see that this width is a milli-electron volt.
So are there two bound states? Are there two bound states? I can see two.
Yeah, there's one and two. I don't know why. Okay, sorry, I'm not so familiar with the details. I don't know why we should have two bound states here and there. I would think that there's only one bound state in the middle. Yeah, thank you. Okay. So now I move to this Fourier theory. So up to this point, we kind of learned that this the ingredient of flow K physics is that you have some very fast driving. So this is again some video from YouTube. It kind of illustrates what the flow K physics, typical situation of flow K physics is. Okay, so yeah, by this video, we know that of course there's a rotating propeller, the rotor, and that the effect of that rotation is to allow this helicopter to float. So in this sense, we're kind of dividing the time scale of the problem into two parts, the slow and the fast time scales. Okay, so in the language of flow K physics, we call the slow time scale as stroboscopic motion. So this movie was stroboscopic. It's given in the period of the frequency of the rotor. So it's 0t, 2t. And you can see that in the slow dynamics, the helicopter is floating. So we have some effective interaction or strength coming out of this very fast time scale motion. The fast time scale is called the micro motion. So that's like the rotation of the rotor, and that's what's happening in between one period from 0 to capital T. And yeah, what we have within that time scale is the flow K state. Okay. Now okay, in this slide, I have few equations. This equation is very, very easy, but it kind of illustrates what the flow K physics means. So I'll try to explain this step by step. Actually, it's so easy. It's so simple. Yeah, okay. So let's start from the one level case, like just a very simple quantum mechanical problem. So I have a wave function psi of k, and then my Schrödinger equation is very simple. I have a function h. So I don't have any matrix. It's just a function, just a real function h. But this real function is time periodic like this. Okay. So we know what the solution is for this Schrödinger equation. You just put this phase or integral on top of the exponential and apply it to the initial state. So initial state times this phase or this phase accumulated, which is the integral of this h. The integration is happens from 0 to t. This t is a small t. Okay, so this, yeah, we know up to this point. The next equality, I'm doing something very strange. So the first part is the same as this part, first part. I'm not doing anything, but I'm adding and subtracting the same quantity, I epsilon t. So adding and subtracting this term. So why am I doing this? And in the next line, I'm writing this into this one. Okay, so sorry that I'm saying this, but okay, so the first term, I'm calling it V. And the second term, which is exponential minus I epsilon t, I'm going to call it exponential of minus I hf of t. But why am I doing this? Okay, so if I define my epsilon in a good way, in a very nice way, what will happen is that my V, my V of t becomes time periodic. Sorry, yeah. H. So if I do the time average, define epsilon as this, what happens is that my micro motion becomes time periodic because after one periodicity, this term will cancel this term, and basically this will become 0. Okay. So yeah, this becomes may seem very, very trivial, but it already captures the important part of properties. Indeed, I can actually apply this to understand this problem of the dynamic localization. So previously I showed this motion. What I was doing there, so I have this one-dimensional lattice. If I write it in the momentum space with k, I have a cosine k with a cosine omega t. So cosine k minus a omega t. If I did the time average of this quantity, actually the time average of cosine is a zeroth order Bessel function, j naught of a times the original cosine back, and I plot here the Bessel function, and you can see that the Bessel function starting from 1 will oscillate and turn 0 at several discrete points. So what I was doing here is to select that a that I will have j naught, the Bessel function, to be 0. This j naught is 0. So I have a flat band, and my breakpoint will be localized and will not move anymore. You also notice so now it's moving. Now it's positive. But if you can see, this wave function is still kind of oscillating. There are small oscillations. That's actually the micro motion. The micro motion is oscillating, but the long time behavior, the spreading out electrons is stopped.
So this is plot in the real space.
This is plotted in the real space. But here I move to the momentum space. Okay, so any questions up to here?
So I guess the key point is to, make this cancellation, right? And as you mentioned in the previous slide, once you cancel that term, then you can.
This term and this term cancels out, and the small t is the capital T, exactly.
Then you get the focus.
Then under that condition, this remaining part is under that condition is weak. So this first part becomes periodic.
And one more question. So from the experimental point of view, which one is more robust, micro motion or the flow clicks?
Okay, that's a good question. So, in many situations, people are interested in engineering this effective flow mechanism to a long time behavior. Like a helicopter, you want your helicopter to float by doing some propagation. But how you do this propagation is a detail. But then some people are also interested in this part. It depends on which aspect you are interested in.
In classical mechanics, there's a term called adiabatic invariance. Is this somehow related to that?
Adiabatic
invariance.
Oh, I don't know. I don't know that word. So I don't know. Thank you very much. Okay. Maybe. So the serial process. Okay, so now this slide is almost the same as the previous slide of the one level system. But the only difference now is that it's generalized to Hamiltonian, which can have a matrix structure or many body system. This is doing the same thing. So I'm writing my time evolution rate. So up to this point we know what it is. This is just a general solution of the Schrödinger equation. But then, under the condition shown that my Hamiltonian is time periodic, I can write down, decompose this time evolution operator into this V and exponential minus I HFT. And the way to do this is, again, to use this definition. So I will define my H of F. Previously, this H of F was the time average of the energy, but now it's defined at time t, capital T, with the time evolution up to that capital T, one period. So this defines the stroboscopic time evolution. And of course, the definition of this Hermitian operator H of F is not unique. So it has mathematical problems, but it's defined in this way. Okay, once I can have this H of F, now it's kind of tricky, but I can define my operator V from my time evolution operator and subtracting this effect of the effective Hamiltonian. So first I define this, and using this HF, I have HF of small t and put it against here as a product the time evolution operator. And the nice property of this combination is since I have this definition of HF, after one time period, my V of t becomes also time periodic. So this V is called a kick operator and it describes the microscope motion.
So that's a good question. So whenever anything that's on the exponential, usually it means it has like 2 pi modulus or something. But in this derivation, it seems like it is hidden somewhere. But I have this question because like when we start from some equilibrium system, we have access to the eigenstate, like at least for ground state. But whenever I try to drive it, then if I have these 2 pi modulus, then I'm not quite sure what is the wave function of my system. Is it going to be a problem?
Yeah, that's not a problem, but a property of the property.
Maybe you should
They can
see here again.
Yeah.
Okay.
Online audience.
Sorry, the question was so. The question is okay, so I'm defining this H of F through this exponential I H of t, and so this makes an ambiguity. So I cannot really uniquely define my H of F. And such that this operator exponential I HFT, this is also not uniquely defined. So there's a problem. Actually, this is known as monodromy problem, but it's a property of local states. After a few slides, I will explain how to calculate for these states in a more detail, and I think you will find out way. There are a constructed way to calculate these operator and states. But again, there's some non-uniqueness in the definition.
Sorry, can you go back one page before?
Okay.
No, one more.
One more.
Yes. So in these operations, capital T is chosen by observer, right?
Capital T is chosen by, so this is part of the definition of the program.
Yes.
This T, so if I have a laser has a frequency and a period of T. So,
Okay.
yeah, it is something we impose to the program.
Okay. Because in small h you don't see capital T.
Oh, yes.
It's additional
So,
parameter.
yeah, this is a condition for this small h. Without this condition, it's just a general Schrödinger equation.
capital T is a period of small h.
Yes, we're solving this radical equation where h is our Newtonian, just a real function. But under the condition that we have a periodicity in h, all these properties are the consequence of having this periodicity.
Okay.
Yeah.
What if the so what if the average turn out to be 0? Then
So the average
the small h,
Newtonian is 0. In that case, the dynamics, so that's exactly the case here in the dynamic localization. This slow dynamics will disappear. Newtonian is 0. We don't have dispersion. The electrons are localized and will not move. Yeah.
Should I, taking a short break?
Yes, that's a good idea. I think this is a good part time.
Yeah, great.
Yeah, this definition.
Okay, so let's thank Professor Osaka for the
So this was the definition of the Fourier states and the decomposition of my time evolution operator into the slow dynamics described by HF and the fast dynamics described by V of T. We call this micromotion and stroboscopic dynamics. Then, so with this definition, let's think about this concept known as Fourier engineering. So the reason that we use the language of term engineering is that we want to invent some device or a situation that is interesting. Okay, so it's like 3 steps. So step 1. Let's start from some trivial material or trivial state, and then apply some external time periodic driving. We can engineer this driving, and by doing that, we want to realize a state with an interesting HF, the stroboscopic dynamics, or in some situations, the time evolution and micromotion as well. Okay, so as an example, so in the lower part, down here, I have this Kapitsa pendulum. Okay, so in the next slide, I will explain this Kapitsa pendulum. The concept is that so we have this ordinary pendulum, but then by having this oscillation, we saw that there is a stability point up there. Now, I'm going to explain how to describe this. There are very famous 2 machineries or tools to study Fourier states. Actually, there are many more now, but in this lecture, I focus on just 2. One is this high frequency expansion, also known as 1/omega expansion or Fourier Magnus expansion. This is very useful. I know that more than 100 papers, theoretical papers, have been written just using this expansion. The second one is sum-based space-time picture. It gives us more deep understanding about the Fourier states. Okay, next slide. So in this slide, okay, I'm sorry that I have some lines here, but this is also very simple. So it explains about this high frequency expansion. So in the first line, I have a definition of the Fourier effective Hamiltonian, H of F. So it is defined through this time evolution up to capital T, where capital T is 1 period. Now I want some expression for HF. Yeah, and how I do it? So I'm doing the most naive thing. So I will take the logarithm of both sides, like this. Then I will have logarithm of this time evolution operator. then you can expand this exponential. So this expansion is a bit tricky, but we'll ignore all the difficulties. If I just do expansion of the exponential, I will get a expansion series like this. So the first term will be the time average of the Hamiltonian, h of t, integrated up to 0 to t. The second term, which is 1 over t, is a time integral of a commutator, h and h at t1 and t2. And then the third one, okay, so you see that there's a lot of nested commutators. I have a three time integral and so on. Okay, so this is like this is a Magnus expansion that we often do in equilibrium physics. Now I use this Fourier expansion. So as I said, my Hamiltonian is time periodic. So I can write it using discrete Fourier modes like this. It's important that I have the time periodicity, which means that I can have this discrete Fourier transformation. I plug in this expression into this Magnus expansion. And then, just doing the integral, you will obtain this kind of expansion series. The first term is again h naught. H naught means the time integral or time average of the Hamiltonian. And then I have h of n, and the commutator is h of minus n. Again, this h of n is defined as a Fourier component of my Hamiltonian. And then this nested commutators will continue. Okay. So this is the high frequency expansion. And in the next slide, I will explain how you can use this interesting example.
So, could you I thought this you have a time ordering.
Yeah, I have a time ordering.
Why do you have all these commutators?
Yeah, exactly. So as you mentioned, or as you say, I have this commutator which comes from the time ordering. So I'm going to switch the order of the. So when you expand this, without the time ordering, you have an integral of t1 and t2, but the order is one. I only have one term, but putting this time ordering, I have a second term which will convert this ordering. So this time ordering is the reason that I have a nested commutator.
So the integration region is always from 0 to capital T?
Yes, the entire integration is only from 0 to t. And t1 is from 0 to t, and t2 is from 0 to t1, and so on.
But if that's the integral interval, then ht1 will always lies in the left, right? Because you have time ordering.
Yeah, this will be the lateral.
Should integrate over a square. That's fine.
Yeah, I
Because
think
you have already
probably
done
if you put in the commutator, probably all the integration region will be from 0 to capital T.
Okay. Now I will. Now I'm a bit unconfident about this.
I believe this is correct. This is the same integral that we encountered in time resolution operator.
Why is not an anti-commutator?
This is the same as, there are two terms, ht1 times ht2 and vice versa. And there's a minus sign between. And so there is a factor of 2 in the denominator. Take care of this 2. So I think this is the same expression that we learned in quantum field theory or quantum mechanics, convolution operator. U. That
I think this is correct. Already for or this time the integral domain.
oh
Okay, maybe this is detail, so
yeah.
I cannot answer it correctly now. Sorry.
You can check later.
Yeah, please, I will check. Okay, then, yeah, so we have this expansion, and using this expansion, I will try to explain this quantum Kapitsa pendulum. Actually, the quantum version of the Kapitsa pendulum is easier to understand. So, our Hamiltonian, currently this is a very dense site. So, let's say I have this pendulum. So, p squared is a kinetic term, and cosine phi is its gravity part. So, this is force that tries to bind it down here. But let's say that this g of t, this equation, has a constant term times plus oscillating term. So this oscillating term represents the oscillation of the pendulum. So one can start from this Hamiltonian and obtain this quasi-stable equation. So in the quantum situation, so I have this t as operator, which is a conjugate of phi, so it's minus I delta phi, and I have this commutative relation p of phi in commutative b minus I. Also, in this Hamiltonian, now my Hamiltonian is time dependent. I have 3 Fourier components. The zeroth component, just the static part, is this usual static pendulum part, and h1 and h minus 1 is there because I have a cosine term. So h plus minus 1 is given by cosine phi, is this term, and proportion to g1. Okay, so just with this 3 component, and I'm just going to plug this into this Magnus expansion. Okay. First, I'll notice that these 2 terms are 0. So this commutator, first commutator, hm and h minus 1, since I have only plus minus 1, and it's the same operator, cosine phi, so they commute, so it's 0. Also here, this term will be 0. Good. Then this h naught, okay, so h naught was the same original term, so this term, but then this first commutator, yeah, maybe it's hard. Sorry, I didn't write the commutation. Yeah. Maybe there's a minus sign or maybe a I. But anyway, so I use this term h naught. I have t squared. It's t squared and h plus minus 1. So we need to say the commutator of t squared and cosine phi. doing the second commutator, I will get sine square. So the sine square of sine, we can rewrite it as cosine 2 pi, and then do something like this. Okay, so now I have a new potential, effective potential, V of effective, and effective project it looks something like this. Okay, so when this blue curve is when this G tilde, okay, so this additional term, when it's 0, I just have the usual cosine term. I only have a stability point down here. But then when I have this cosine term, and if that's large enough, I will have a quasi-stable point around phi plus minus pi, pi or minus pi. And if you start your time evolution around here, the state will be like quasi-stable. Of course, in quantum mechanics, you have a tunneling probability to escape from here to here, but it takes some time. Okay. So was this clear?
Question.
Yeah.
So how stable is the beta stable?
Yes,
How
yes.
stable?
Okay, so I mentioned that you can have a tunneling probability to be out here. No one has really studied it. We know that we have a potential, potential like this. I imagine that my lifetime of staying here is limited by this quantum tunneling probability for its inverse.
Experimentally, they believe forever, almost forever. From the experimental point of view, I mean, those nature papers, they can observe this phenomenon for a long time. Right?
Yeah, that nature paper is using a different, more simple rocket physics than this one.
But still, it's a long time.
It could be a long time. If this was realized, it could be a long time.
And all the time scale is related to this potential area, right?
This barrier.
Yeah.
So you have a wave packet here and then contours here.
So that could be very system dependent, right?
Or parameter dependent.
Yeah.
Actually, we wrote on paper studying the stability at this point. Many body pizza pendulum. If you have many pendulum and you couple to each other, then you would have instability and instant. Thank you. Okay. Half of the ball is already broken. The last part, I will try to explain this okay turning later, how to understand this physics. Okay, so yeah, I'm going to explain this physics. I also showed you this animation. When you have a honeycomb lattice, so graphene, by a circular porous laser field, the graphene will turn into a quantum pulsate. Actually, to be more precise, this system in the high frequency regime, it will become equivalent to the Haldane model. The Haldane model, it's a lattice model. It's just a honeycomb lattice, but with a nearest site and next nearest opening, where this next opening has a phase factor of 5. This phase factor will recognize the force of symmetry and make the system be a term insulator. Get a quantum force state. Let me explain this. So step by step. The first, so there are two ways to understand this. One is the real space picture. Maybe this is easier. Okay. So I'm going to use the first commutator, Hn and H minus n. And I'm going to explain what's the physical meaning of this. Actually, this will turn out that this first commutator is something known as a laser-induced popping. Laser-induced popping. What do I mean by laser-induced popping? Okay. So now I have many lines. So my Hamiltonian is so simple. It's just a tight binding model. T daggers, Tj, T I and Tj. And I have this hopping term, J. But as I mentioned, I have this higher space. So my hopping term is a complex number and it's time periodically oscillating. The phase is a circular force-like can be written like this. It's basically just oscillating around and around in the xy plane. This L is this direction of hopping. I have three directions, 0, 1, 2. And for those three directions, my hopping has a different phase. Okay, so starting from here, let's think about this laser-induced hopping. Actually, what I'll do is very simple. I'm just going to Fourier expand this hopping term, so this higher space. If I just do a very simple Fourier expansion with this discrete Fourier mode, I get my coefficient. Again, I will get this Bessel function, J of n, and some phase exponential, which I 2 pi m L n over 3. Sorry, L is the direction of the hopping. So it depends on the direction you hop. Okay, so after this is like this is a laser-induced hopping. Okay, then I will move to this real space picture. Now let's imagine that I'm at this blue point, starting from here, and I move from here to there. But during this process, okay, so in the static case, I will just hop with the zeroth component. So my m, this integer m, corresponds to the number of photons I will absorb when I hop from here to there. So I'm moving from here to there. The n corresponds to the number of photons I'm going to absorb. So if I absorb one photon, it's going to be H1. And if I'm going to emit one photon, it's going to be H minus 1. Okay, so here, there. Then from there, here, I am emitting photon. Okay. So by doing this process, so this combinator Hn, H minus n, I have a process of this n was 1, n was 1. I'm absorbing one photon and emitting one photon. I have two components because this is a combinator. The other component is I'm going to first emit one photon and then absorb one photon. That's the other component. This combination, so if you plug in this to here and to the commutator, gives this effective next unit hopping with space. So this is how we can map the honeycomb lattice and the circular prototype, the Hardane model. This was the first explanation. I moved the second explanation in the momentum space. Maybe this is easier. So in the momentum space, let's focus on a Dirac Hamiltonian. So sorry that this is a bit too small. So sigma x and sigma y, and my kx and ky, but I have this oscillating electric field. That's this A cosine omega t and A sine omega t, which is oscillating around and around. If I do this commutator, in the momentum space, is h1 and h minus 1, you can see that they correspond to the Pauli matrix of sigma plus and sigma minus. So if you calculate this commutator, you obtain sigma z. And the coefficient is a squared over omega. So I have a gap opening in a two-dimensional Dirac system. Actually, it is known that in 2D, two-dimensional Dirac system, the gap opening will imply the parity anomaly or quantum Hall effect. You get a non-trivial Berry curvature, and this Hamiltonian is already enough to show that I have a quantum Hall state. I will explain this Berry curvature again later. But okay, then so actually in this experiment in countries of darkness, they claim that they see this gap open down here. A bit difficult to see, but the main claim of this paper was that they found a small gap opening around here. But you also see that there are many other features. So that's these replica bands that's up there and how they hybridize and so on. So next, I'll try to explain that physics. And to do that, so I'll explain this other tool, machinery, known as the space-time picture. So, sorry, yeah, maybe this is again a bit complicated. This is another way to understand this Bloch physics. It's more similar to the usual Bloch theorem. So what I will do is to start from the Schrödinger equation, and I have this time periodic Hamiltonian. Okay, so this is all we have. The interesting thing is that I can map this Schrödinger equation into a eigenvalue problem, to a steady state problem. So to do this, I need this assumption. So my solution, psi of t, should be written in this Bloch form. You can recall the Bloch theorem. So my wave function psi, that's the solution. You can write it as a product of exponential minus I x on t, the phase term, and this phi of t. This phi of t is a time periodic wave function, and we call this the Bloch state. Actually, the reason that we can have this decomposition is the same as the reason that we can decompose our time evolution operator into the kick operator and the Bloch effective Hamiltonian. It's actually the same statement. And then this so by just plugging in this expression into the time-dependent problem, I will get this eigenvalue problem. For my new Hamiltonian H is given by the original Hamiltonian minus I of sigma I delta t, the time derivative. So, okay, then we go one step further and do a Fourier transformation. So we expand this eigenvalue problem using Fourier components. So my Hamiltonian like this. Then you use this discrete Fourier expansion and write everything. But rewrite my program into this comes like this, where okay, so this phi is the phi of m is the m's Fourier component of the eigenvector. So we have a infinitely large Hilbert space, and my Hamiltonian is again a very big Hamiltonian. My h of mn is really the Fourier component of the Hamiltonian with additional term n times omega. This n times omega, which comes from this I derivative, the time derivative, is counts the number of photons that is absorbed in this state. Yeah, maybe we should do. What's the time? Yeah, sorry.
So, when I try to transform the eigen system for this y, because of this yt plus f(t) is equal to yt, that's the okay state. Is it possible that I can experimentally prepare some okay state? Because in the equilibrium situation, we can lower the temperature, so we got the ground state. But in this case, can we do like are there some way that we can have a pure state as for this okay state?
So occupation of these Fourier states are like, determined by how your system is coupled to the dissipation source. And yeah, we think that some of the states. So in the next few slides, I'll show you some Fourier bands. Some of the states can be like, occupied when you couple the system to electron bands, but some are not. So when you couple the system to a heat path, this coupling is static, but your Fourier state is time evolving. So when you when the electrons from the static state occupies those Fourier bands, they will be mixed into different Fourier states, even when their energies are similar. So then it will be like some density matrix, incoherent state. So yeah, occupation of Fourier bands is really a system-dependent phenomenon. Yeah, sorry, this is a bit detailed, but it's good to see this in an example. Okay, so this is a Hamiltonian that I explained in the previous slide. I'm just trying to show this graphically. So now I have a big wave function with many Fourier components. And this is my big Fourier Hamiltonian with many off-diagonal terms, which are coming from the Fourier component of the Hamiltonian. So I'm supposed to diagonalize this big Fourier Hamiltonian. Then, okay, so this is the pictorial picture or illustration of this Fourier space-time picture. So going back one slide, so this big Hamiltonian. Okay, so if you have experience in lattice system or crystals, you start to think that this Hamiltonian is a Hamiltonian of a layered material like graphite. What do I mean by that? So I'm starting from a very simple, say, two-dimensional graphene, but I'm applying this laser field. So laser field gives us this two-dimensional electron system. The big Fourier Hamiltonian that I showed previously, it has the original two-dimensional system described by H naught, but it also has a coupling between different Fourier bands or Fourier replicas with separated in energy by omega, omega 2 omega, or minus omega, minus 2 omega, the hybridization is given by the Fourier components H1 and H minus 1. Now, this big Hamiltonian, it looks something like graphite. So a three-dimensional stacked layered material. And indeed, yeah, it has a very, very strong resemblance. And with point is this direction, this new artificial direction, the lattice is given by the Fourier component M. So if we trace that, I have this index M. This was nothing. So one size. It comes from this Fourier M. So I have a three-dimensional lattice program with this artificial direction given by the Fourier component M. Another big difference is that we have this energy shift in this M direction, which is given by omega. We have this because so that have this shift of omega. So I have a component. And so in this way, so in this picture, we can also understand this effective Hamiltonian H of F that we already discussed previously as a situation that we are trying to separate the energy scale. So let's imagine that this omega is large enough. So energetically, these other bands are very far away. So these bands are far away, and their effects are very weak. So we can take into account the excitation and relaxation process as an effective term. And we're just focusing or projecting inside our original two-dimensional system. That's how we have constructed the Fourier effective Hamiltonian using the Laplace expansion. Then, then
Very quick question.
Yeah.
So it seems like when I have this Fourier drive, I kind of create a artificial dimension. So how about the Fermi-Wagner theorem? Like, can I have one dimension system, and one side, in principle, there's no phase transition, but once I drive it, it turns out that you could have some breaking. There studied or.
Yeah, so I will explain the last part. It will be like a Saurus pumping. That's equivalent to a adiabatic pumping. Okay. So this is the. So I'm going to explain this for number 3. So let's understand how to calculate the Fourier band. So for this very simple example, a two-dimensional Dirac cone driven by circularly polarized laser light. This is very simple, but very educational. So our Schrödinger equation, if I write it explicitly, is 2 by 2 Hamiltonian. Very simple. Diagonal is only 0. Off diagonal, I have k bar, and k is this complex number. Then I have a exponential I omega t, and it's conjugate on this off diagonal components. That's the Fourier. That's the driving coming from the lasers. Then, so as I mentioned, we are supposed to write very big Fourier Hamiltonian. It's going to be like this. I will explain it in the next slide. Here, and you see. So the first diagonal component, I have 0 k bar 0. That's the static part of our Hamiltonian. K bar shifted by omega outward. Then, so down here, I have a shifted band down here, which is again shifted by minus omega. Actually, so I'm truncating my Hamiltonian here, but in the real situation, this is an infinitely large Hamiltonian, so I should have a larger system and numerically truncate somewhere. Then, so if I focus on the off diagonal blocks. So here I have 0, A, 0, 0. Down here I have 0, 0, A, 0. So that's like a sigma plus and sigma minus. Right? And if you include them and just diagonalize this big Hamiltonian, you get this spectrum. So this is a Broca spectrum as a function of momentum k, and this direction is quasi-energy epsilon. So first of all, this is so related to the bands that we saw in this experiment. And it's the darkest. They see this Broca side bands. They also claim to see this gap opening and so on. And also a small gap opening at the graph by just numerically diagonalizing this big Hamiltonian, you can easily obtain and such Broca bands. Okay, so any questions up to here? This is easy.
Can you remind me what A is capital A? B.
So A is the gauge field, and gauge field is related to the electric field. So E is the F. A is F over omega, where F is basically E, the field strength of the electric field. So, what's the physical consequence of this Broca dance? So, as we already mentioned, there are some ambiguities in this Broca spectrum. So it's very similar. So we have this William zone structure that the spectrum are going to repeat itself again and again. So there is a Broca state in a periodic lattice. We have a time periodic perturbation, and we have this periodicity in the energy direction. And the same state will appear again and again in the energy direction. This is the ambiguity which is inside this Broca physics. The point is that so although we have infinitely many states in this big Broca Hamiltonian, they're not independent. Actually, they're the same state appearing again and again. Yeah, which is kind of related to this ambiguity in defining the Broca effective Hamiltonian. Then another point. So once we know what the Broca bands are, we can calculate some physical response how about this? I just mentioned one work that we did. So it's about the Kubo formula. So if you're interested in transport induced by laser fields, so you know that the Kubo formula, the original Kubo formula, it's a linear response theory. It will explain the transport property of a system in equilibrium. However, one can extend the Kubo formula to a Floquet state into a driven quantum system. The assumption is that our quantum material, so let's say graphene, is strongly driven by this laser field, A of AC. This A of AC is very strong, very big. But then, due to that effect, its transport properties changes. So we want to perturb it by adding an extra small additional electric field, say E of DC. This is an extra perturbation, and we want to understand the linear relation between this DC electric field and the current. This coefficient sigma can be obtained using the Floquet states. And so in this paper, also actually there was a previous paper in the study of microwave-driven zero resistance states, a study in quantum core system. It's possible to generalize the Kubo formula for Floquet states. Now it looks like this. So if you remember in the textbook how the Kubo formula looks, this new Kubo formula looks exactly the same, or almost exactly the same. But the difference is in the detail. So first of all the quantities appearing here are given by Floquet states. So this epsilon is now the Floquet quasi-energy, and this state phi is the Floquet state, so time periodic Floquet states, and the average, so expectation value is given by a time average inner product. And the a little bit difficult quantity is this occupation fraction of the Floquet states. Even now, we don't have a real universal way to calculate this occupation fraction. In equilibrium, we know that this occupation for a free fermion should be the Fermi distribution, but in a Floquet state, this distribution depends on how your system is coupled to dissipation. But with that ambiguity, I can write my Kubo formula like this, and using the same algebra, I can write the whole conductivity in a TKNN form. So I have the daily curvature term, and it's given by the Floquet wave function. So
this works for any
sorry?
this works for any
Yeah, this formula works for free fermions or weakly interacting fermionic system in any dimensions. Yeah, for this first expression, and this TKN formula. Yeah, you're interested in the XY component of the whole conductivity. But you just change the momentum integral to 2-dimension or 3-dimension. So for this example of a honeycomb lattice under circular porous light, if you calculate the Betty curvature, it looks something like this, where it has a peak and fringe like structure like this. So yeah, it's this part, the Betty curvature part. You have this big peak, and basically this peak, we have this analytical form, and this size and height of this peak is given by this gap opening at the drag point. Okay. So that was the main part, and then I own a few remarks. So up to this point, we have been focusing on this Floquet effective Hamiltonian eta vector. But the idea of Floquet engineering is more broad, and there are many interesting examples that we get a non-trivial topological effect. So the so-called Floquet topological initiator, we deal with the topology of eta vector in the momentum space. We have other topological effects like pumping, Powers pumping effect, and the anomalous Floquet topological initiator, which discusses, which is characterized by the topology of U of K. So this is one time derivative at one time solution operator. V was a kick operator. The topology of the kick operator can be non-trivial. So each of them will define a different class of topological states in the Floquet state. I'll show you just a few examples. The first one is the pumping effect, Powers pumping effect, using the language of Floquet physics. This is also very easy to understand. So one simple model to study the Powers pumping is this so-called time-dependent Rice-Meller model. So the one-dimensional lattice system is they have A and B sublattice. So there are two atoms in one unit cell, and let's say that the on-site potential of A and B are oscillating with sine omega t, and the hopping term between this first part and the second part, this bond and the second even and odd bonds, they're also oscillating with cosine omega t. So if I consider the slow limit of this oscillation, there will be a current being pumped in this lattice. Actually, in the language okay, space-time picture, the original one-dimensional lattice is mapped to a two-dimensional lattice system like this. Okay, so you understand this? So it's like this graphite or layered system. So my original one-dimensional lattice is here. Then I have a stack of them, another one here and another one there, and they are coupled to each other through this time-dependent hopping and time-dependent potential. So the bonds that goes in the vertical directions are the potential, and the hopping that goes in the for the next unit, next type is oscillation of the coming from the oscillation of the hopping. I have this two-dimensional lattice model. This two-dimensional lattice model now has a complex. It's a Hermitian system, but it has a complex hopping, and it turns out that this system becomes a two-dimensional quantum Hall insulator. So if you calculate the band structure, it will have a gap and a Bailey curvature. And then I also mentioned that in this artificial dimension, there is this static electric field omega in this m direction, So this electric field omega will generate a Hall current in the x direction. This Hall current, okay, so the Hall conductivity of the system is given by the Chern number, which is 1. So I have a 2 pi over h bar times 1 Chern number. I have a quantized force on the 50, and the current will be quantized proportional to omega. We remember that omega, so remember that omega was like 2 pi over t. So for each periodicity, so for one period, I will pump one charge in this system. That's the like way to understand how it's pumping. Then there's another class of topological states. I only show one, right? It was invented by Mark Wagner and his collaborators. So actually, it's already a long time ago. So they're interested in the topology of the equilibrium part. So this high frequency motion. Actually, in the language, we can see this. This very nice picture. So this is the band in the quasi-energy band plotted against momentum. So let's say that I have one H in my material. So if I have a Floquet Chern indicator, the Chern number of 1 and minus 1 for these two bands, then I can have a H state, higher H state. So this is a very trivial Floquet state. But then let's imagine that I'm going to change my omega. So this small omega is now my frequency, and I'm changing this omega. Let's say omega is becoming smaller and smaller in this way, such that at some point the upper edge of my band will touch this boundary of the Boolean zone, like this. Then, if I continue it more further, what will happen is that this band here and this band here will start to hybridize and gap out. In such situation, we can have state that the Chern number between this band and this band is interchanged. This means that originally I have Chern number 1 and minus 1 here, but my Chern number will exchange here to the other band, and my Chern number can be 0 and 0. However, the interesting part is that the Chern number can be 0, but in this situation, since I already have one H state here, I would have another higher H state connecting this band and this band up here. Yes. So this is a state that does not exist in the original period space. It relies on a very special fact that my quasi-energy space is periodic. So meaning that this energy at minus half omega is equivalent to plus half omega. Using that periodicity in the energy direction to the Boolean zone structure, I have this extra H state. So this kind of new topological state is called the anomalous Floquet topological state. One can kind of characterize this using binding numbers.
Yeah, there's a one possibility for the case. Even for today, the number 0, but we know it's possible there's no A state for the case.
Sorry, can you repeat again?
For the case, it's possible that there's no A state in the circuit.
So initially, if there was no Chern number here, so like 0 and 0 and no H state, if I connect here, okay, so I wouldn't have this, but then I can interchange my turn number, and I have a edge state here, but not here. And this turn number will be like 1 and -1. That can be.
Say it says a no trivial case.
Oh yeah, it really depends on the material, and you can have many combinations. What the turn number tells you is how many edge state will go into this band from up minus the number of edge state that goes out. The turn number will give the number of this minus this. So here it's 1 minus 1, 0. Here it's 0 minus 1 minus 1. You can have like, many other combinations.
Without interaction means the freeze doing that.
Now, like a shrinking omega like this, and my zone boundary is touching this back. My omega is being smaller and smaller and smaller. Yeah. Relatively, my here, my omega becomes small. And touch this edge. Again, yeah, this kind of illustrate. If you see this in the open William zone. So if I repeat this again and again and again, then yeah, we have a copy of the same state again and again. It's kind of not so exotic. Having a term represents the number of edge states when it's in and out. So this is a new type of proposal state.
Question is, like there's a when we talk about the logic space, the edge correspondence. So in this case, it seems to be kind of strange. Your form is like the number 0, but somehow you still like some robust edge space. So how to understand that?
There's a winding number that characterizes this edge state.
So it's not a Chen number. That's
It's not a Chen number.
I see.
Wave function, like the winding number.
So the 1 minus 1 is topological equivalent to 0 minus 0, or
Here,
that's 1 minus.
1 minus 1 is 0. Here,
I mean,
0 minus 1 is 1.
how about 0 minus 0?
0 minus 0 can be 0. Yeah, you can
It's
have
equivalent to this one.
you can have a very trivial state. Turn number 0, 0, no edge state at all. That's also okay.
But equivalent, topological equivalent to this one. 0 minus 0 is equivalent to the topological equivalent to 1 minus 1. It is 0 minus 0 topological equivalent to 1 minus 1.
No. So that's the point. So there's an additional topological number, the winding number, which will count the number of edge state during here. So the point is that in addition to the Chern number, we have an extra topological number justifying the topological state in a flow case system.
What is the winding number? What is winding number?
Yeah, I think it should be 1.
So winding is winding in the time direction.
In the time directions. Okay, so it's a good time.
That's a good question. So if it is a winding in time direction, is it just
generalization in the spatial direction in a trivial way, or it is completely different?
I think it's very related to finding the space direction. Okay. Cool. Yeah, so that's a remark. So you can also apply the idea of block engineering to interactive systems, like a multi-integrator. And yeah, okay, so you know that if I have a multi-integrator, the low energy degrees of freedom is the speed. We usually have the high density. But if you have like a laser radiated multi-integrator, your Heisenberg coupling J here, and this term, and also will be modified by the laser. You also get an additional term, spiral hierarchy, which breaks time reversal symmetry. It's called S, which comes like this. So you can use this machinery to predict or to control the spin structure in a multi-integrator. This is one very interesting direction that people in experiments are now trying to proceed. Also, let me advertise my collaborator, Kimura-san. He wrote a very interesting paper, Tamura Oki. I think this is one of the very, I was very surprised about this paper. He showed that applying circular polarized laser to high DC Cooper's, so Hubbard model, in the D-wave superconductor, you can turn it into a D plus IB topological superconductor by opening a gap at the gap polarization. Okay, so with this, thank you very much. So this was the goal of this lecture, 0, 1, 2, 3. I hope you were able to understand something. Yeah, and if that's done, I'm very satisfied for this. Okay, so thank you very much.
Lectures, and I encourage students and postdocs to ask questions. We have short time, a couple minutes for questions, and then we have a lunch break. Please. Only student postdocs, professors late. Please, I want to hear. See the hands up. Dr. Kim Raymond. No? Others? Well understood? Yeah. Okay, so now open to everybody. Any other questions? Yeah.
Other possible effects. Think about circular polarization is that it breaks time reversal symmetry, and there will be difference between left and right circular polarization. So you can get some results which you know that it's coming from rocket physics. If it's just linear polarization, you get excitations, and very hard to see what is happening. It's whether you're getting rocket physics or just laser induced heat in it, and so on. So okay, the answer is no. I don't know any like topological states that was obtained by linear polarization. Mention. So at least there was one interesting experiment. Okay. So, and I know one experiment, not porosity state, but related to this dynamic localization. So we get a lot of Bessel functions. This occurs in linear polarized vacuum. A Bessel function will shrink. So when you apply laser, the popping becomes weak. So in an experiment in Japan, so they started from an interactive system. So you have popping and interaction. They claim that by having a very strong laser field, the popping becomes weak, and the interaction relatively becomes stronger, and you go into a older phase. So it's something like a laser-induced cooling in the older insulating phase. That has been seen, and they claim that this Bessel function resonates 1, but we can go down to maybe 0.1, sorry, 0.8 or so. In holistic physics.
Okay, so I think we could open questions from the online audience. Anyone online would like to ask questions, please speak out. Any questions from the online audience? Is there? Oh, yeah, some, yeah, chat.
In the beginning, you show us right that separate the from into different regime with respect to omega and T. But it looks like the okay as long as the nucleus period. Is this correct? Okay. So you remember the first part. So yeah, indeed. Could you repeat the questions? Okay, so the question is, so it's about the I showed this data like this, and I said that the Fourier physics is good around here, but the Fourier theorem itself, it should be applicable to everywhere in the phase range. That's correct. But so, yeah, then that's a difficult question. The Fourier theory is applicable everywhere, and indeed, actually, Kelvich used equivalent to the Fourier theory and moved from this multi-photon regime to the tunneling regime. That's what Kelvich did. So he actually used Fourier theory and moved in between the two regimes. So indeed, Fourier theory works. But then the pictures that I described, like this space-time picture and a picture of high-frequency expansion, they both rely on large omega limit. And when omega becomes smaller and smaller, there's a problem. Okay, so when omega becomes smaller, so in the case of high frequency, of course, our high frequency doesn't work. It's small omega by definition. Our space-time picture, what would happen is that when omega is small, our different bands will start to be on top of each other energetically. So there will be like a transport in this artificial direction. Okay, so that's okay. But So the example of this Saurus pumping, we study the small omega limit. So Saurus pumping is the physics when omega is very small around here, and we have two-dimensional lattice starting from a one-dimensional lattice. So we get some interesting physics there. Okay, so yeah, maybe it's really just Blocky physics can be applied everywhere, but this multi-photon picture is good in the large omega limit. Maybe that's the correct way to answer. Thank you for the question.
Okay. Any other questions? Maybe one more question or comments from the audience.
I have a question.
Okay, so if not,
Someone is
there is one question.
Yes, may I?
Yeah, please.
Oh, okay. In the next few slides, you show an idea of dynamical localization. Yeah, can you remind me what's the idea behind? I didn't get the idea of this.
It's really very easy. Is that time average? Okay, so the question is, what is the idea behind dynamic localization? And the point is that our predicted slogan Hamiltonian like this. So have this extra Bessel function J naught. It's very easy to understand this Bessel function. It's the time average of the higher space. Exponential minus I is cosine t. If you take the time average of this, you get the Bessel function. When the Bessel function is 0, this is the growth of the Bessel function. When A is 2.4, so that's somewhere here, my Bessel function becomes 0, and my Hamiltonian becomes 0. When a flat dispersion and the electrons are localized, they don't have motion.
Sorry, I didn't hear very clearly.
Oh, I didn't. I should. Yeah. Sorry. Okay. So one more time. So the point is, it's the time averaged Hamiltonian. So the problem dynamic localization is very simple. The higher space. So you see this exponential of minus I a cosine omega t in the first line.
Yes.
So that term, if you time average it, you get the Bessel function.
Right.
Right. And this Bessel function becomes 0 when capital A is like 2.41.
Okay.
You see the Bessel function on the right lower panel, and
right.
It can be 0. And when it's 0, the effective Hamiltonian is 0. So there's no, it's like a flat band, like in a Landau level, and the electron motion is frozen. You have no dispersion.
No. In the first line, I think the Hamiltonian becomes kind of constant, right? That's what you are trying to say.
Yeah, momentum in the air. The derivative of K is the velocity. And the velocity is 0.
So I don't hear any voice.
Sorry. Okay. So here. Okay, so the bands are flat, and the momentum derivative, the K derivative of the band gives the velocity, and the velocity becomes 0 when the Bessel function is 0. That means that the motion freezes.
Okay.
So is it clear? This Bessel function J0 of capital A vanishes when capital A is about 2.4. And when that happens, the Hamiltonian HF vanishes, and you get the flat band, and so the electrons cannot move, and they are localized. And this localized state is driven by this laser field, right? The AC field, and that's why we call this dynamical localization. This localization is not due to Anderson localization, but due to the dynamical driven field. Is that clear?
Yes.
Okay, great. If there's no further questions, thanks our speaker.